And A, B, B, C, free response 5. This is one of those problems that you walk into and you see a whole bunch of words, and sometimes that's really intimidating. It really is just a giant chunk of words, but here we go. At the beginning of 2010, a landfill contained 1,400 tons of solid waste. The increasing function W models the total amount of solid waste stored at the landfill. Planners estimate that W will satisfy the differential equation dW dt equals 1 over 25 times the quantity W minus 300 for the next 20 years. W is measured in tons and T is measured in years from 2010. Part A. Use the line tangent to the graph of W at T equals 0 to approximate the amount of solid waste in the landfill. The landfill contains at the end of the first 3 months of 2010, meaning when T equals 1/4. Okay, so time out before we panic about the wordiness. Part A fundamentally just asked you to find a tangent line equation and then use it. So deep breath, doesn't matter that it looks wordy. We know that when we're asked to find the equation of a line, we need 2 things, forever and always. 1, we need a point, right? So that point in this problem is going to be T comma W, right? And the second thing we need is a slope, which in this problem is going to be my dW dt evaluated at whatever that point is. And I'm just going to put it as point for now, right? That's what I need to find. So let's walk through what they gave us. They told us the tangent line when T is 0. Okay, cool. So that means in this problem we want 0, comma, whatever W is at time 0. Well, they tell us in the first line of the problem that the amount of solid waste in the landfill at the beginning of the problem is 1,400 pounds. Tons. That's a lot more solid waste. Sorry. Part 2 here, right, to find our slope, we need to evaluate dW dt at the point I just found, which is 0, comma, 1,400. The big mistake people make here is they accidentally plug the 0 in for the W, right? We're not plugging in 0 because there's no T in this equation. We're plugging in W. So I'm going to get 1 over 25 times the 1,400 minus the 300, right? So I'm going to get 1,100 over 25, right? Which, couple different ways to do this, right? I would suggest the easiest way to do this is to say this is an 11 times 100 over 25, right? Because 100 over 25 is a 4. So you get this a 44. There's other ways to get there. Okay, so my slope is a 44, which means that my equation, the first thing I was asked to do, right? So my tangent line equation is y minus the y value, which was the 1,400, right, equals m, 44, x minus the x value, or t minus the t value, but I was going to do x minus the x value, right? So the tangent line equation I'm going to get is y equals 44 times the quantity x minus 0 plus a 1,400, sorry. All right, cool. So if you want to use t, that's fine. My argument is if you're using y already, then you could use y and x to stand in for your tangent line equation. They use t, I use x. It should be fine either way. That's my tangent line equation. So I want to now approximate. They specifically said use t is 0.4. So my w of, sorry, not 0.4, 1/4. My w of 1/4 should be approximately what happens if I plug a 4th in here. So 144 times a 4th plus 1,400, which is going to be a 1,411, and that's in tons, right? So when you see multiple prompts in a single part of a question, do me a solid and make sure you go back and check that you did every part. So use the tangent line, so here's the tangent line, right, to estimate the amount when t is 1/4. I did that, great, and I made sure I put units. So 1,411, cool. Part B, find d squared w dt squared in terms of w. Then use that quantity to determine whether your answer for this is an over or under estimate. If they're telling you to use the second derivative to determine something, that means that whatever they want is determined by concavity. So we'll talk about that in a sec. So the first thing I'm supposed to do in part B is find the second derivative of this thing in terms of w. So part B, d squared w dt squared is going to be, now it's up to you if you want to distribute this. I'm going to argue that I probably would have treated this as a 1/25 w minus a 300 over 25. And I know I could figure out what 300 over 25 is. It's not a big deal. I get that it's a 12, but I don't really care because I'm going to derive it away anyway in a sec. So when I derive this, I get 1/25 times dw dt, because I'm not deriving with respect to w, minus a bunch of 0. But they said in terms of w, so I'm going to have to replace this dw dt with the 1/25th W minus 300. So I'm going to get 1/25th times a 1/25th times the quantity W minus 300. And that answer is totally fine, right? If you want to make it look slightly nicer, that's great. Like if you want to leave this as your d squared W dt squared, right? There's nothing wrong with that. You're right, d squared W dt squared. If you want to clean it up, great. If you don't, it's fine. So if you want to clean it up, I think a lot of us do know what 25 squared is. If you don't, that's fine. It's up to you. It's a 1/625 times this W minus 300. Okay, so either of those answers are fine. Now I'm asked to use this answer to determine if my previous approximation is an under or overestimate. So here's how concavity helps you figure out if tangent line approximations are under or over. When you forget this, because we all do, and I don't actually have it memorized, I just draw a picture, you know this is about concavity. The reason you know it's about concavity is they asked you to use the second derivative to figure it out. So it must be about concavity. Knowing that, just draw the two situations. If I have something concave down and I draw a tangent line, you can see that the actual is under the approximation, right? Because the tangent line is the approximation, and this is the actual, right? So if something's concave down, then it's an over approximation. If something's concave up and you draw a tangent line, you can see that the actual is higher than the approximation, right? So essentially, this thing must either be concave up or concave down, right? So if this thing is concave up, I know that I'm looking at an under approximation, and if this thing is concave down, I'm looking at over approximation. Well, here's the thing I know. I was told that W is an increasing function, which is like a sad state of affairs, but we all know it's true. The landfill is getting more waste, not less. So W is increasing, and I know that W of 0 was 1400. What that means is that W minus 300 has to be a positive number. There's no way W minus 300 is negative. What that tells me, since 1/625 is also a positive number, is that d squared W dt squared has to be greater than 0. So W has to be concave up, right? W of t is concave up, and my estimate was an under approximation, just like this picture shows. So my estimate in part A, right, that was part A. So my estimate in part A was an under estimate, right? And you want to use their wording, and they said underestimate or overestimate, so it was an underestimate, okay? So again, it's about concavity, and if you forget which situation's which, just draw it. It's what I do every single time, and it served me well for the last 20-some years. Part C. This makes sense. It's a separable differential equation. They're going to make us solve it. So this is where most of your points lie. Part C, find the particular solution, W equals W of t, meaning you're going to have to solve your answer for W to the differential equation that you were given with the initial condition W of 0 is 1400. So anytime you're handed a separable differential equation, meaning you can multiply or divide to move all the variables to their respective sides, it's likely you're going to be asked to solve. So I'm going to leave the 1/25th over with the t, and I'm going to divide the W minus 300 over. So for my part C answer, I'm going to get dW over W minus 300 equals the 1/25th times the dt, right? If you don't separate the variables, you're done. You don't get any credit for this, and this is usually 5 to 6 points on a question where you're asked to do it. So make sure you separate the variables. I'm then going to do the antiderivative of both sides. This is a simple natural log. Technically, it's u sub, but if I make u the W minus 300, my dW is just, my du is just dW. So this is going to integrate to the natural log of the absolute value of W minus 300. I'm going to walk you through in a sec why I don't need that absolute value logically in this problem. On this side, I get a t over 25 or a 1/25th t, it doesn't matter, plus some constant c. I'm already going to argue that I don't need this absolute value here. The reason I don't need the absolute value is I was expressly told that W starts at 1400 tons and doesn't drop. W is increasing. So I can get away with just dropping this absolute value because W minus 300 is not a negative quantity. But it doesn't really matter. So I'm going to solve. Now, I can either plug in and find C now, or I can solve and then find C. Doesn't matter. It's a different approach. So I'm going to go ahead and show you what happens if I plug in W of 0 equals 1400. Right? I'm going to get the natural log of 1100 equals 0 plus C, right? So it looks like my C is the natural log of 1100, and that's fine. I'm going to show you a different way to do this in a sec. So I get that C. Now I'm going to go ahead and buy myself some space. I need to solve for w. So I have this natural log of w minus 300 equals t over 25 plus the natural log of 1100. Cool. I'm going to exponentiate both sides, which is going to give me a w minus 300. Again, I know it's positive already anyway because w is larger than 300, equals e to the t over 25. Now, you could leave this as plus natural log of 1100, but most of the time we rewrite it as an e to the natural log of 1100 because that's how you deal with variables that, or that's how you deal with exponentials. When you have the exponent has a sum, you can split it into two different terms, e to the t over 25 times e to the natural log of 1100. These guys are going to cancel, just giving me an 1100. So I'm going to get w minus 300 equals 1100 e to the t over 25. And then I'd add the 300 over, and I'd get that w of t is 1100 e to the t over 25 plus a 300. That answer's great. The other way you might see that answer is if you didn't bother to do what I did here, you might see this as an e to the whole quantity t plus 20, or t divided by 25 plus the natural log of 1100, and then all of that plus a 300. And that's also right, totally fine. All good. So either of those would be fine. Now, an interesting side effect is that if you don't feel as comfortable with this, there is a way around that if you solve for w first and then find a different c than the c you started with. I've done this in other videos, so I'm just going to retrace my steps for a sec. Let's say, rewind to here, w minus 300 equals t over 25 plus c. Let's say instead of plugging in, I decide to solve for w first. So I exponentiate, right, and I get w minus 300 equals e to the t over 25 times e to the c, which I'm going to rename as some different constant c sub 1. So I get w minus 300 equals c sub 1 e to the t over 25, right? So w equals c sub 1 e to the t over 25 plus 300, and then I could go ahead and plug in my point 0, 1400, and I get 1400 equals c sub 1 e to the 0 plus 300, which is how I get that 1100 for my c sub 1, and I get the same answer, w equals 1100 e to the t over 25 plus a 300, right? So either way you go, you end up with the same answer. It's just a different